Speed and velocity, we talked about it briefly yesterday. The main thing I want you to take away from that discussion is that speed is always going to be a positive value. Velocity can be positive or negative, because velocity is something where direction is taken into account. And generally what we say is that if an object is going towards the origin, towards the 0 point, that is a negative velocity. But speed would just be positive no matter what. And in terms of this class, we deal pretty much exclusively with velocity. So, questions on worksheet number 1?
No, it was really easy. It took 2 minutes.
Well, that's good. So, number 1, you can see the graph there. Who's traveling faster, A or B?
A.
How do you know?
Steeper.
It's steeper, yep. And the slope of a position time graph tells you your velocity. Backside, you can see the new graph on the right. Letter B and letter A are both represented there. Which one has a higher velocity?
Yes, A.
Yeah, in terms of, I suppose it would be different for speed and velocity here. If you have a higher slope that's going negative, that would be a larger negative velocity. And in terms of speed, it would just be a larger value altogether. So yeah, I just want to make sure you're aware of the differences between those two things. If we're talking about speed, speed is just whatever the number is. Velocity can be positive or negative. And if you look at the graph on the right side, the slope of A is much larger in the negative direction. So that would be a very large negative velocity under those conditions. Any other questions? Alrighty. I'll come around and get that from you.
I do have a question, actually.
Sure.
How are you doing today?
I'm doing real good. How are you doing, Pete?
You know, I want to make terrible.
Well, that's not good.
No, actually not that bad.
Did you have to see Mr. Barr take a test or quiz or something?
What?
During the last hour?
No, last hour?
During resource?
Oh, no, I just need to watch everything.
Right. That's where it was.
Yeah.
I was going to ask you if you took a test at that one.
Oh, no. Thank you. I think I'm taking something soon. I don't know.
Okay. Thank you. You're welcome. All right. New stuff today. It's kind of a new take on the same old story from last time. Instead of talking more about position time graphs, today we're going to be talking about velocity time graphs. And then you're going to get a little piece of homework that you can probably finish in the span of about 3 minutes. So, let's get this underway.
Yes, let's do it. I like this today.
Yeah, not bad so far. What's that?
Is that all going to be easy?
You know, the stuff we're learning today is going to make up about 2/3 of what this chapter actually is. So if you're good with today and yesterday, you should be in really good shape. Basically, so here's the thing. Today we're talking about velocity versus time graphs. And ultimately we'll be practicing going between position time and velocity time. The only extra step we take after that is including acceleration versus time graphs. And that's really what all this chapter is.
Do you ever have to convert the graphs into the other type?
Oh yeah, like I might give you a velocity time graph, and at the end of this chapter you'll be able to make the other two. Or if I give you a position time graph, you'll be able to make velocity and acceleration. So, it's a neat little chapter. If you're really good with graphs, you'll have an easy time with it. But if you just keep up normally, it should be much easier than, force diagrams and force equations. So, all right, so in terms of our velocity time graphs, well, let's make sure we're aware of some notation here. Of course, S would stand for speed. V is for velocity. And both of those two things, of course, are both measured in meters per second. It's the same idea with both. And the only difference between these two things, you don't have to put this in your notes, but they're both found by taking change in position over change in time. But this position represents something different for each of them. For speed, it would represent how far you've actually gone total. For velocity, it represents your displacement, how far away you are from where you began after the whole thing started. So yeah, that would be a different value for each. But for the purposes of this worksheet and the purposes of this section, generally we just say speed is always positive, velocity is both positive and negative. And we spend a lot more time talking about velocity than speed. So, if I say this, what does this say? Change in velocity. And is change in velocity final minus original or original minus final?
Final minus original.
Final minus original. Very good. Final velocity I denote with no subscript. Original, I have a little O for original. And that's it for vocabulary there. Is that all right with you guys that we don't do much with vocabulary in physics?
Yeah. Well, definitions.
Okay, so now we'll just jump into a few graphs, and that's about it.
No.
So we've got two velocity time graphs there. And what we're going to do is just put some basic scenarios onto these two graphs, kind of like what we did yesterday. So the first scenario is the absolute simplest. We've got our origin right here. Donatello is right there. And time begins right now. And time stops. So you're not moving anywhere, you don't have any velocity. So if I'm putting this on a velocity time graph, I would begin down here, because when time begins, I have no velocity. As time goes on, that velocity is unchanging. So my graph would just look something like this. So there's our constant velocity of 0. Something else to be aware of is yesterday we did the scenario where, we started away from the origin, and time would begin right now, and time would end right now. So at rest, away from the origin, do you think that would look any different from this? No, because this is a measurement of velocity. This does not say anything about position. So if we start at rest and we end at rest, it's going to look like this regardless of where we do it. So yeah. New scenario. Time begins right now. Time stops. So Donatello is moving with a constant velocity away from the origin. I'm seeing everybody go like this. So maybe it looks something like that. Anybody have any different answers?
Wait, no, a constant velocity on the top.
Oh.
Yeah.
Okay. And Keegan, yes?
It might be dumb, but like, So is the 0 like a 0, or does it stand for original location?
This just is a 0. Yep.
Yeah, just horizontal.
Yeah, Gavin caught it here. Because this would tell us that as time goes on, our velocity's growing. Donnie started with a velocity, and he kept that constant velocity through the entire period of time. So yeah, this is what it would look like on a position time graph, but this ain't a position time graph. So we'd start up here, and it would look something like this. And this kind of brings up another important thing to note here, and that is, how do we know it's a positive velocity? Anybody catch that? I think I mentioned it briefly earlier. Yep. When an object is moving away from the origin, we call that a positive velocity. If it's going toward the origin, it would be negative. So, for the sake of argument, if we were doing the same thing starting over here, and it was going towards the origin, that would be a negative velocity, and it would be a horizontal line down here, under the 0 point in negative territory. So, okay, those are the first two graphs. Two more coming at you. Now, we're not really going to dive too deep into changing velocities right now, but I do want to get these in your notes. They're not going to be examples like this on the homework. I just want you to see exactly what an acceleration looks like on these graphs, even if we're just going to touch on it today. So let's say time begins right now. Time stops. So Donatello started with the velocity of 0, and as time went on, that velocity grew and grew and grew.
That's gonna be this one.
Yeah, that's going to be this one. So a couple things we need to take note of this. So this is a constant acceleration. Obviously, we are speeding up. And so we would say that Donatello is accelerating here. This all seems straightforward so far. You'll see why we have to be specific in the next example. And this is also a positive acceleration. And you can see that it's a positive acceleration in the same way that you could tell on a position time graph why we have a positive velocity. It's a positive slope. So if you have a positive slope on a velocity time graph, it's going to correspond to a positive acceleration. Just like a positive slope on a position time graph corresponds to a positive velocity. So let's do the other scenario then. We're going to start at the origin again. But here, time begins right now. Time stops. So he began with a very large velocity, and as time went on, he slowed down. So, it's like you have some kind of gang sign there. Down like this?
Yeah.
Okay.
Do we have this? No, no.
Max is gang affiliated.
Figured as much.
Yeah.
So, yeah, we're going to be starting up here and going down because we start with a large velocity, and that velocity is positive because we're starting by moving away from the origin. So we start up here, and as time goes on, that velocity decreases, ultimately reaching 0. And there are a few things we need to point out about this type of motion here. Same thing as this scenario. This is also a constant acceleration. We define acceleration as any time your velocity is changing. So even though we are slowing down, we would still call that an acceleration. It's kind of a blanket term.
Isn't that called deceleration?
Yeah, we're getting to that, yep. So we are slowing down. And so we would say this object is decelerating in the way that this one was accelerating. But they're both accelerations, because acceleration just means a changing velocity.
That's so weird.
Yeah. Furthermore, this is a negative acceleration. I'm sure you would have guessed that. You might be wondering, why don't we just say this is all one thing, you know? Negative acceleration is always slowing down, positive acceleration is always speeding up. But we have to be specific, because you can have a positive acceleration and be slowing down. You can have a negative acceleration and be speeding up, because it all changes based on what direction you're going. If you're going in the negative direction and you're speeding up, things get a little complicated. So just because we're slowing down, that does not always mean we have a negative acceleration. But in this case, it does. So ultimately, whether your acceleration is positive or negative simply depends on the slope. So, questions on this so far? Couple other things to take note of here. Yesterday, with our position time graphs, we talked about what those graphs actually meant. What does the slope of a position time graph actually tell us?
The velocity.
Yeah. And so we can actually figure a lot of things out from these graphs too. Any guesses on what the slope of these graphs tells us?
The deceleration?
Yeah, you're on the right track. It tells us the overall acceleration, whatever that number is.
So, both of them combined?
Yeah.
No, I'm just saying stuff.
Well, yeah, both of these, it will tell us that acceleration, whatever that number is, positive or negative. So if I found the slope of this, maybe it was 10 up here and 2 down there. Rise over run would be 10 over 2, which is 5. And because it's going down, it would be negative. So that would tell us that we have ourselves an acceleration of negative 5. And acceleration is measured in meters per second squared. And this is also on your formula sheet and your formula t-shirt. Now these velocity time graphs tell us more than a position time graph and later on an acceleration time graph. We can find 2 things just based on this one graph. The other thing is if we look at the area that's trapped by this or this. And when I say trapped, I mean the area that is trapped between that line and the 0 point. If we calculate that area, it actually means something. Let's just, for argument's sake, let's say again this is 10 and this is 2. What would the area of that triangle be?
20?
Almost.
10. Oh, God.
Yeah. 1/2 base times height. So 1/2 times 10 times 2 is going to give you an area of 10. So the question is, what does that 10 actually tell us? If you're ever curious on this, one thing that you could do is when you're doing the math here, add in the units. and see what happened to the units. So this 10 is in meters per second. So I'm going to do this same math, but without numbers. I'm just going to use the units. So 10 is in meters per second. This 2 is in seconds. What are the final units?
Meters per second squared.
Nope. Just meters. Because this seconds is like it's on top. So it's going to cancel out with what's on the bottom there. And you're just left with meters. So it's a pretty strong indication. Yeah, if we can figure out this area, that tells us exactly how far we've gone. So velocity versus time graphs are important. You can tell a lot from them. Questions on any of this so far? Okay. I'm just going to run through a couple examples that kind of tie in with the homework, and then you'll have plenty of time to get this all finished. This homework could very well be easier than the last one. As I'm erasing this, one of the things we talked about briefly in one of my other classes today was if you could, they were talking about how we should have nap time and recess in high school.
Yeah.
My question would be if you had to pick one of those, which one would you pick?
Nap at what time?
Recess.
I don't know. Recess.
Recess was always the best though. Recess was plus like it would like help me get out some energy. Yeah. Recess.
Yeah. How many votes
I
for
freaking need energy.
how many votes for nap time?
Me.
1,
If I
2, 3, 4,
grab
5,
one
6, 7, 8.
Nap time.
How many votes for recess? 6, 7, 8.
Can you
Wow.
nap during recess instead of going to recess?
Nah, for the purpose of this, I would just say you have to pick
Can
one.
you do recess during that time?
So that's pretty evenly split. That's interesting. Okay, so a couple things. On the worksheet, you're going to be dealing with velocity time graphs. And because velocity can be positive or negative, most of your velocity time graphs are going to look more like this than that L shape. This is the 0 point. This would be positive velocity. This would be negative velocity. So let's just say, for fun here, let's come up with a scenario. So let's say Donatello starts over here, and time begins right now. Time ends. So he has a constant velocity going towards the origin. How would that look on the velocity time graph?
Horizontal.
Horizontal line underneath? That's exactly true. Because the velocity is the same the whole time, so this number isn't changing. And because we're going towards the origin, that's indicative of a negative velocity. If you're going away, that would be positive. So there's that. Let's...
What
Yeah.
if it's just horizontal on the origin line?
Right here?
Yeah.
That would just be no motion. It's holding still. It could be holding still in front of the origin, on the origin, away from it. It would all look that same, yep. How about this scenario? Watch closely. Time begins. Right. Now. Time ends. So you're holding still for most of the time.
That's gonna be.
And then you move at a very high speed
I got you.
after a while. Keegan.
So it's okay. So it's gonna be like in the middle of like T. Start like in the middle of T. Like
In the middle of T?
Oh, wait, hold on. Like, can I just do it?
Yeah, sure.
It's like it's really. I'm bad at explaining things. Sorry.
No problem.
I feel like it would be a line at 0, and then in the middle it would just spike up and.
Like that. Okay.
Crap! I'm sorry.
No problem. So,
How do we get there, geeks?
yeah, this is true. Up to this point, you're holding still. Absolutely. Now, Donatello picked up speed extremely fast. And once he reached that really quick speed, he maintained it. So this is really close to the right answer. I would probably say it's something like, because he increased his speed very, very quickly, maybe something like this, and then after that maintained that really high velocity.
How does my car go that?
So it looks something like this. And for the purpose of the worksheet, a lot of times they say like instantaneously he starts moving at a really fast speed. So it looks something like this on your worksheet if you're going through it. And if, let's say, you start with a big negative velocity, you'd start down here, and then maybe you suddenly stop because you smash into a wall or something. Your line would go like this. You'd have a dotted line, and then you'd have your straight line right there. Your velocity for this worksheet will always be a horizontal line. All right. One more just to make sure we got this all wrapped up. The back side of the worksheet. You have to convert from a position time graph to a velocity time graph. This seems intimidating the first time you see it, but that should be the only time you're intimidated by it. Because once you see this, this should be pretty straightforward from here on out. So, this is a position time graph. And what does this tell us about velocity? How do we get velocity out of this?
I mean, it's a constant,
And then it's
positive.
0.5 meters per second.
Close. So, on a velocity time, or on a position time graph, the slope tells us the velocity, right? So the slope of this, rise over run, 10 over 5, is going to be 2. So if this slope is positive 2, that means for the first 5 seconds, we have a constant velocity of 2. What's our slope here? 0. So our velocity after that point would just be nothing. Should we do another one like that? Just to make sure we're all good? Let's do one more. Let's just look at this one. What's the slope of this? Negative 1 slope. And that slope tells us what the velocity is going to be for those 10 seconds. So, yep. That's what your velocity time graph would look like then. Your slope is negative 10 here. That means your velocity is going to be, if your slope is negative 1, your velocity is going to be negative 1 for the entirety of that graph. Questions? Alrighty.